Corrosion is undesirable oxidation of metals. Oxygen oxidizes other things. That's why it's called oxidation. Oxygen's easily reduced. And so metals are especially subject to this. So the corrosion of most metals is going to be spontaneous when paired with the reduction of oxygen. Now that's not going to happen under all conditions because you have to have things set up correctly. We still use metals as building materials. We make cars out of metals. We use all kinds of things. We make all kinds of things out of metals. And in spite of them being in the presence of oxygen, acid, and water, they don't just like disintegrate on us. Some metals, like aluminum, when they oxidize, they form a very hard oxide coating on the metal, and that prevents additional oxidation from occurring. So this is why aluminum is often sort of a dull finish. It's not super shiny because it's reacted with oxygen to form some aluminum oxide, which is a very tough coating and prevents the further oxidation. So aluminum protects itself. Iron doesn't do that. Iron forms a flaky oxide, and so it forms the oxide and then that flakes away, exposing more iron underneath, and it'll just keep going until all of the metal is oxidized away. So you all have seen rust, right? So here's a metal building that's got rust all over, iron siding on this. So the rusting of iron is actually a rather complicated process here, and I'm not going to test you on the details of this, but I think it's helpful to understand, just have a basic understanding of what's going on. So you have to have some moisture present in order for rusting to occur. So here we have a droplet of water on this iron surface, and electrons are produced by the oxidation of iron to iron 2+. So we've got that happening. Where is that happening? Down here. So we've got the iron being oxidized. Yeah, oxidation occurs at the anode. I was looking at the cathode. I don't know why. So we're making some iron ions there. And those ions are going to travel to the cathode and react with oxygen and hydrogen ions. The hydrogen ions come from carbonic acid that's formed when carbon dioxide dissolves in the water. And then those iron ions can travel through surface moisture and get further oxidized to iron 3. Yeah, that's up here. And so then you're forming this iron 3 hydroxide, and it's a hydrate. It has some water molecules associated with it. So the rust that you see is actually a hydrated form of iron 3 oxide. So you can't really just say, okay, well, this is the chemical formula for rust, because there are lots of different varieties of rust. So how do you stop iron from corroding? Well, you keep moisture away, because water is a reactant in that last reaction, and also you must have some way of conducting the charge, right? And that happens in the water. If you have extra electrolytes, like in Minnesota where they put salt on the roads, then the water that gets on the car has some salt in it, and the salt conducts electricity better than just the water from condensation. Or if you're in the coastal, along the coast where you've got a lot of seawater, ocean water spray coming up and getting on your car's going to rust a lot faster than if you're not in those places. The presence of acid also promotes the rusting because that enhances the cathodic reaction. So water, acid, and salt are bad for your car. Preventing corrosion is a big industry. One thing you can do is keep the iron dry. So it could be coated with something, such as paint. That's what they do with cars. You paint the car to keep it from rusting. But then when you get chips in the car, chips in the paint, it'll rust there. Another way to do it is by using a sacrificial electrode. So that's what's illustrated up here. You've got a sacrificial electrode made out of a metal that's oxidized more easily than iron. And so instead of the iron corroding, this sacrificial electrode corrodes instead. You can also coat the iron with a metal that will oxidize more easily and then have a nice protective coating. Galvanized nails have a thin layer of zinc. When zinc rusts, it forms zinc oxide, which is stable and acts as a coating, much like the aluminum oxide does on aluminum. So galvanized nails aren't going to rust in your fence. Non-galvanized nails are going to rust. Any questions about corrosion? You've got electrochemistry occurring in your body as well. You've got tiny pumps in your nerve cells that pump ions through membranes. You get a concentration gradient that is formed, a concentration gradient of sodium and potassium ions, and that results in an electrical potential of about negative 70 millivolts across the membrane, and that's considered the resting potential. That's just like regular. When the nerve gets stimulated, channels open that allow the sodium ions to flow into the cell, and the potential goes up to about plus 30 millivolts. And then other channels open to allow potassium ions to flow out, bringing the potential back to near the resting potential of minus 70 millivolts. So we get a spike in an electrochemical potential in one area of the membrane, and that triggers a spike in a neighboring region. It's a little bit like doing the wave at a football game or something. You got this spike, and it makes the area next to it spike, and so that spike travels down the nerve. So the electrical signal moves down the length of the nerve cell. At the end of the cell, you've got a chemical electrotransmitter, which is released, and that travels across that synapse, thank you, to the next nerve cell, and then stimulates the same kind of electrochemical spike in the next nerve cell. So it runs down that cell, and at the end of that cell, neurotransmitter goes to the next. It's actually very complicated, and yet it works amazingly well. Another application of electrochemistry is one variety of breathalyzer. So measuring the quantity of ethanol in your breath to see if you are too impaired to be driving a vehicle. So the suspect breathes in here, the ethanol from their breath is going to change the magnitude of the current that's produced. And so it'll give a digital readout of your blood alcohol level. This is the reaction. So ethanol plus hydroxide ions. So the ethanol is being oxidized and oxygen is being reduced. So it's actually, once you cancel out all the common things, it ends up being relatively simple. We've got the ethanol plus oxygen. Oh wait, that says gas too? That's acetic acid. So the ethanol is oxidized. Of course, that fuel cell needs to be calibrated, but it can be used to precisely measure blood alcohol level of a suspected drunk driver.